Anyway, so let's get on. As I said before we started recording, that the main point is my input and outputs are functions, and I have an operator written here. And what we're going to do is to find a surrogate, something that approximates this operator fast, right? And this is going to be my G star. And the main point that we sort of realized in the last lecture is that you can't just use inputs and outputs. This is too sort of low a bar, inputs and outputs functions. This is too low a bar because you can essentially interpolate anything to get that. So instead, we also need some notion of continuous discrete equivalence. What does it mean? It essentially means that even if, and we'll see that repeatedly in today's lecture, the lecture next week, that functions are continuous objects, not continuous functions, but continuous in the sense that they're continuum. They represent the continuous objects. But in practice, and this is important, we don't have access to continuous objects, right? Means on a computer, we have to necessarily discretize. So practice, we have discrete representations. And sort of the interplay between the two, how are continuous objects and the discrete representations interacting with each other, this is going to be sort of a core concept, a core issue that we have to deal with. Okay, so in the last lecture, I finished by saying that how do traditional numerical methods do? Means what sort of learnings, what sort of teachings we can take away from traditional numerical methods. And if you remember, whether it is finite difference, finite volume, finite elements, spectral methods, and so on, we were able to rewrite them in the following paradigm. And this is what is very important here. Let me recollect or recapitulate what it is. So remember that my operator is a mapping from X to Y. So this is a mapping from X to Y. So it takes a function and it maps onto a function. But what do traditional numerical methods do? So we took finite elements, we took finite difference, finite elements, and also spectral methods. All three of them, also finite volumes, is exactly in the same category. I just didn't have the time to, it's completely analogous. I did not have the time to write it. But the basic idea is the following. So first, what you do is that you start with an infinite dimensional space and you project it down to finite dimensions. And this is done through what is called encoding. Okay, so you take something which is infinite dimensional and you get it down to finite dimensions. Once you are in finite dimensions, you could do whatever processing that you want to do. And this is where we use the underlying physics, the OD, PD, SDE, and so on. And you can map any finite dimensional object to another finite dimensional object. And finally, you want the function back, so you go back to infinite dimensions. So in other words, your G here, this mapping, is approximated by three objects or three operations: encoding, approximation, and reconstruction. Okay, so this is G of U is approximated by this object here. Sorry. So first you take this object here, for instance, for finite elements, what did we do? We started with the function and then we were able to take out the node values of the function. And then we evolve them. So then we come here to this step here. And for finite elements, why is this not working? Yeah. For finite elements, this was our scheme. So this was the inversion of the stiffness matrix. If you remember, this was A inverse B. And then you obtain the node values of the solution because you are able to invert the stiffness matrix. And then in order to realize it at any point, you just interpolate it using a Galerkin basis. So this was sort of the basis of finite element methods, right? And similarly, for spectral methods, we do the same with respect to Fourier coefficients. We evolve the Fourier coefficients, and then you do a Fourier interpolation. So it's exactly the same idea over and over again. So in fact, we will keep on, sorry. We'll keep on doing this the whole of today's lecture, that we are going to play with this construction, with this diagram that I just showed you. So given something which is infinite dimensional, we project it down to finite dimensions, we do some processing in finite dimensions, and then we go back or lift it up to infinite dimensions by using some suitable basis. Now, what is the issue? So traditional numerical methods, they clearly are able to do it. But the issue is that our objective, so recall, let me write it down here, recall, So the aim is to learn operators from data. So in principle, we need not even know what kind of equation it comes from. It could be Laplace's equation, it could be heat equation, Schrodinger's equation, whatever. And more importantly, we suppose not to know what are finite elements, finite volumes, finite differences, right? So we have to take into account this data, and we will be able to learn the operators in a supervised manner. So that's the idea. So this part here is not available to us. We don't know this, right? Because this is, after all, the physics that tells us how to build this approximation, this finite dimensional processing. We don't have that. We also don't know what the bases are going to be. Means how do we encode the function? How do we reconstruct it? All this is unknown. So this in principle has to be learned from the data that is given to us. And this, how we make these choices, how we choose this E, how we choose this A, and how we choose this R, this gives rise to different kinds of operator approximation, operator learning algorithms. And this is what I'm going to describe today, also in the next lecture. So let me start with the first one. I just sort of simplified it by calling it as operator learning or op-learn architecture. And this is what is called SNO. So what is SNO? Means this is not historical at all, as you will see in the later pictures, but it is sort of pedagogically, it makes sense. So this is what is called a spectral neural operator. It was only from last year, but it's a very neat and easy idea. Spectral neural operator, it is invented by these Russian computer scientists. And the idea is the following. So also they themselves don't sort of present it in this manner. This is my personal interpretation, just to present it in the course, right? So remember that the idea is that we are going to find suitable approximations of the encoding, of the approximation operation, and of reconstruction, right? So the idea is, in this particular case, what we're going to do is we are only going to learn what we can learn, and we're going to put in a lot of prior information. So what are the priors? The prior that we are going to put, and follow it carefully. So we are going to use the prior. Prior is that we will fix a basis. Fix a basis for x, y. These are your function spaces a priori. So this is the important thing. Okay, so just imagine that my function spaces, these are subsets of L2 square integrable functions. And I fix a basis a priori. For instance, these particular individual gentlemen, they chose the Fourier basis. So Fourier basis is essentially sines and cosines, and you could also write it in complex. So phi k of x, this is my basis. This, for instance, could just be trigonometric functions. 2 pi I k dot r. Sorry. Yeah, 2 pi I k dot x. So this is just a trigonometric basis. If you want to think in real terms, this is just cosines and sines, right? And sine k pi x. You fix this basis. This seems to be a limitation, but it will turn out that it is not such a big limitation. And it's anyway first method. And remember, where did we encounter the Fourier basis before? Spectral methods, right? So in spectral methods, the basis is given by Fourier basis, which is this complex exponentials, sines and cosines. So you fix it. So you fix it both for the input as well as the output space. Of course, needless to say, you can fix a slightly different basis for the input or different basis for the input and output. But just for simplicity, we fix the Fourier basis. So now how does it work? So because we have fixed a Fourier basis, so given an input, let me A, so this for instance could be in X, which is a subset of L2. I know that I can always rewrite it as, or not exactly, but approximately, because otherwise it would be an infinite basis. Let's rewrite it as, so this is K of A K phi K of X, right? So this is going to be your basis expansion. So expand the function in an infinite basis, and then it is exact. But of course, it cannot be exact. We make some error. So what I'm going to do is we are going to approximate it by a m term truncation here. So this will be a k phi k of x. So depending on how smooth the function is, how fast its Fourier coefficients decay, I can make a good approximation or a bad approximation. Okay. In particular, if my functions are rough, the Fourier coefficients decay slowly, and the approximation is going to be bad. If my functions are smooth, they decay quickly, and my approximation is going to be good. So my E here, the encoding operator, takes what it returns is equal to AKs. So this k from 1 to n. Very easy. So this is also what you do for a spectral method. Given a function, you just project it onto a Fourier space and you extract what are called the Fourier coefficients. So this is why the encoder here has coefficients. Okay. Now, similarly, at reconstruction, so at the reconstruction level, so what we're going to do is that we have this AKs. So this gives me an AK. I'm going to do a finite dimensional approximation, and I'm going to produce some uj, for instance, uj. So uj's are some basis elements now. So I have some vector j from 1 to p, j from 1 to little p. So this is going to be the product of this particular step. And this will be my coefficients, which I'm going to reconstruct. So R, this operator here, applied to this basis coefficients, uj, will give me simply uj phi j of x, j from 1 to p. Okay, p and m are some numbers. These are hyperparameters. Okay, so what is the idea here? So at the input level, given a function, you extract some Fourier coefficients, you're going to process them. So Fourier coefficients are a vector, you process them, and you extract another vector, and then to lift it back to functions, you just use the Fourier basis to interpolate. Okay, so this is the reconstruction here is done with Fourier. You could change it to Chebyshev or some other Hermite or some other orthonormal basis. There are many choices that are there. So this is also taken care of. So what is left now, and this is exactly what we do in spectral methods, right? Remember, in spectral methods, we extract the Fourier coefficients and we lift them back into physical space by a function space by using the Fourier interpolation. So what is left now is so these are fixed, right? Means we of course have a choice in the hyperparameters because you choose what m and p are, but other than that, these are fixed. Now, all that is left to do is to take my basis coefficients to input and map them to the basis coefficients in the output. And we were doing that for traditional numerical methods from the physics itself. Like we took the Laplace's equation, wrote it in Fourier space, and then we were able to relate these two, right? But now we don't know that. But what we know is sure as hell, this guy here is a function which is going to map vectors to vectors. And we know that any function, so remember that DNNs are universal. This is very important, which means that we can map any function, continuous, but even measurable functions, function to function, which means that I can approximate this mapping with a DNN. So this is where a DNN comes in. Okay. So this is the DNN. So what is the algorithm here? Let me just, I will summarize it in a bit. So you fix the Fourier basis on both input and output. So given, I will write it down in a minute. So this part is just the extraction of the Fourier coefficients. Use a DNN. So this, of course, has to be trained from data. It has its weights and biases. And then you pull it back to function space just by using the Fourier coefficients. So is this algorithm clear? All that I have done is to replace in the spectral method the use of the scheme by a DNN. So this is all because I don't know what the scheme is. I don't know what the physics is. And this I'm going to approximate it by a deep neural network. So let me perhaps summarize this. Maybe I should have used. Okay, so let me just summarize what a spectral neural operator is, and then you can ask me, or I'll ask you some questions. So we have spectral neural operator, SNO. So remember that input is A, output is, let me call it as U star. So what are those steps? Encoding. So here I take A and I'm going to produce E of A. E of A is a vector, UK, K from 1 to M. And these are just the M Fourier coefficients. m Fourier coefficients of A. So remember that this is not going to be an exact representation of A because we are going to make errors. So now tell me, how do we find the Fourier coefficients? So given a function, how do we extract the Fourier coefficients? Yeah? Who is going to say that? Come on. Given a function, any function, you should all know, everyone here is at least an engineer or a physicist or a mathematician. Or yes? We can do the Fourier integral. Okay, so now we are talking, right? So this is so given a function A, we compute the Fourier transform of A. So Fourier transform of A is now a function, it's not a function of X, it's a function of frequency K, right? And this is the integral over whatever space that you're dealing with, D for that matter, of, it depends on whether you normalize or not. I'm using an unnormalized version. So f of x, e to the power minus 2 pi I k over x. So k dot x, something like this. But of course, we are not going to evaluate this integral, right? You know how difficult it is to compute Fourier transforms? Means I know because when I was a graduate student, I had a test where I had to compute only Fourier transforms. The whole test was computing Fourier transforms. I had, this was the lowest ever marks that I got in my life. So out of 25, I got 6. And the reason is it's very difficult to compute them. I missed only one trick, later on I realized the trick and then I could have answered all the questions, but I still remember it because it's difficult to compute Fourier transforms. So how do we do this in practice? Yes. This is a possibility, but this seems like an onerous possibility. Means there is a much faster, particularly if I have D to be my Cartesian domain. How can I get the Fourier coefficients, or how can I do the Fourier transform quickly? Yeah. Yes. Come on. Yes. DFT or FFT. DFT is fine. So we have to do what is called the discrete Fourier transform by the algorithm called the fast Fourier transform. Okay. So even before any machine learning, this is very, very essential. You should learn how to do Fourier transforms very quickly. Actually, no one writes these algorithms anymore because whatever scientific programming package we use extracts these things very, very quickly. So you have to take a Fourier transform, a discrete Fourier transform, and extract the Fourier coefficients. So that's the first thing. Then the second step is what is called approximation. Let me call it like this. Approximation is that you take these Fourier coefficients. Okay, that should have been AK. I don't understand why I said UK. So you take these numbers here, AK, this vector, K from 1 to M, and you go to A of these vectors, AK, and this is a DNN, a deep neural network. So here you fix whatever weights and biases, and you're going to train these from data. And finally, the reconstruction is, so given these numbers, you just sum them up. So this is equal to, let's say, UK, K from 1 to P. And then the reconstruction is very simple. This is U star is simply equal to the sum P from, no, K from 1 to P of UK of your basis functions. Since I don't like writing complex exponentials, I will simply write them as Pk. Okay. So to compute or to sort of implement this algorithm is, as you can see, very, very easy. All that I need to do is to use discrete Fourier transforms, how to train neural networks, and then I extract the solution out of it. Okay, so it's a very, very simple algorithm. It has issues with it that I'm going to tell you in a bit. Perhaps you can yourself identify the issues, right? Because it is sort of constraining. Computationally, it's not very challenging, particularly if you're on a Cartesian grid. If you're not on a Cartesian grid, computing the Fourier transform is much more expensive. For instance, the algorithm that you said could potentially be used for that, but yeah, but as I said, it's not as easy as you are on a Cartesian grid, right? But more than that, there is a conceptual issue here that we're assuming that the Fourier basis, by the way, I just said it for Fourier, but in principle, you could use any basis here. So let me write it down. Let's call this as generalized spectral neural operator. Generalized spectral neural operators. How am I doing with respect to time? Not very well. Generalized SNO. You can take any basis. So essentially freedom to choose any basis. But this has to be done a priori, basis, so as a plural. A priori, and why is that priori? So in particular, so you have X and Y are your input and output spaces. So I can choose a basis phi k here and a basis psi j here, right? And I can do the same algorithm, but now with respect to these bases. But for instance, I could, for instance, on the input space, I could choose Fourier basis. On the output space, I could choose a Chebyshev basis. And that will clearly, why would I do that? There could be some advantages. You'll see some examples that in some cases, one basis is better, in some cases, another basis is better. But essentially, all the learning happens in a finite dimensional manner. There's no learning of these bases, right? The basis is already something that we are providing due to expert knowledge. For many, many problems, one can actually prove that the Fourier basis is optimal. Okay, think about what sort of problems there are. But this, so this is a sort of an easier algorithm in some sense. And by this, you can do operator learning because any function to function processing can be done. Whether it sort of satisfies our continuous discrete equivalence, this we will see in a later lecture. The answer is yes, it does, right? Because all the processing is happening in a finite dimensional manner. So the infinite dimensional aspects are covered by some traditional signal processing, harmonic analysis, and so on, and they're here. Okay, but the issue, as I said, is that, so what is the big issue? So perhaps we should put that in red. Issue is finding basis a priori. You need to have some expert knowledge in order to be able to do that. Okay, and this can be, as I said, limiting. There are also computational issues that I just alluded to. So there is a way in which you can generalize this, or you can get out of this limitation. And again, I see that things go slowly. Okay, you can get out of this limitation. But before I move on, are there any questions about spectral neural operators, about just this construction using these basis functions and extracting coefficients and processing them? Yes, she's saying. How do you find more? I will tell you that. I will tell you exactly how to train these objects. Okay. So first I'm just defining the models, but perhaps after the break, because I will first define a few models, and then after the break, because training them is exactly the same. So I will spend 10-15 minutes on how do you train them, how do you define the loss function and everything. So I will come to that. Okay. I'm now just defining a model. Just like with deep neural networks, if you have an MLP or a CNN to define a model, at the moment I'm just defining a model. But I will talk about training. Yes.
When you say train the approximator with data, you mean that we have an example of an A, an example of a U, we discretize them, and then we train.
I will also, this is again a question about training. I will definitely, perhaps I should have said it right away, but my plan is to say it soon. Okay, and then your questions will be automatically answered. My sort of rather limited point was, does anyone have any questions about the architecture itself, not about how we train? Yes. This is a very, very good question. There are, it depends on how much of expert knowledge do you have, right? If you know, for instance, that your data is generated from some spectral method, then you know that sine and cosine is, or you have some periodic structure, then you know that sine and cosine are good examples. Otherwise, any basis, as long, it depends on the function space. You cannot do operator learning in a vacuum. You have to know what is the function space that you are dealing with. If it is L2 to L2, perhaps Fourier basis is as good. But it is, how do we know what is optimal, right? We don't know that. And this is precisely the reason, or precisely the segue to the next topic, which is when we don't, or we want to learn the basis too. And this leads to another set of architectures, which are very popular, which are called as, this is why I said I give you some models and then I'll tell you exactly how to train them. But this is now the moment to talk about what are called operator networks. A little bit of history about them means these operator networks, they stem from a paper in the 1990s by two Chinese computer scientists, Chen and Chen. And this has been sort of revived in more recent. They were dealing with shallow neural networks, right? In the 1990s, no one was able to handle deep neural networks. No talking. So, and then in 2020, a couple of years ago, people said, okay, let's use them with deep neural networks. And this became what is called as DeepONets, which are very popular operator learning architectures these days. And the idea is, it's not that they thought of it in the way that I'm telling you, but the point is, as I said, as many of you said, what is a good basis, right? So just like, okay, we don't know what is a good basis. Why don't we also learn it from the data? And this is precisely what is done in DeepONets. It looks very complicated, but it's sort of a rather simple architecture. And the basic idea, so let me just put it down already. The idea is learn the basis too. Learn the basis from data. So this is the basic idea. You can also learn the basis, right? So what is the, okay, there are several figures that I have put here. Maybe the relevant one is this one, because this is just I don't understand why it became so small. Didn't look like that when I was looking at the slide myself. Okay, so now what do you do with then? I have even written down things here so that it's very easy for me to talk you through this. So what you do is, again, encoding. So remember that earlier we were extracting Fourier coefficients, Chebyshev coefficients, and so on and so forth. This is a much simpler encoding. This could be limiting, right? Because it could be expensive to do a Fourier transform, particularly in non-Cartesian domains. This is a very, very simple encoding. For instance, if you remember, if you go back to finite differences, so the encoding is simply take the point values of a function. And this is what it does. So compared to spectral neural operators, which extracts a basis, coefficient, by the way, also extracting point values is extracting a basis coefficient. But so let me just explain this. So what is the encoding now? So encoding is given a function u or a, sorry, input is a. So choose a set of points. Let me call them as xi, perhaps. I from 1 to, now I'm out of capital I maybe. So these belong to the domain that you have. So take your domain. So you have a domain. Even if it is Cartesian, the distribution of points need not be, it could be grid points on a Cartesian domain, but it could be some random points for all I know. Could be. But fix these points, okay? And I'll tell you why it is very essential to fix these points in a minute. So choose them. And so the encoding E takes a function A and simply extracts the values of A at these points. Xi, I from 1 to, well, I shouldn't have said I, right? I have used M. Good. So this is M. Good. So I from 1 to M. So what have I done here? Instead of taking, I just fix a set of random points. And I could be grid points, maybe not necessarily be grid points. This is one of the advantages of this. It's very flexible, right? Earlier, we had to do a DFT in order to compute, extract the Fourier coefficients. But now, given a function, we can always read out its values at a set of grid points. It's very, very easy. And this is what you do. You read out the values at these grid points, and that is your encoding operation. Now, regarding the approximation, well, let's look at the reconstruction because we could also look at approximation. So approximation is you take these AIs, so this is equal to A little I. You take this vector AIs, sorry. It's not so easy to write on tablet. So AIs, so you take these and you extract, I think I call them as, even I can't see. How can you? Beta. Okay. So I extract a vector beta k from 1 to b. So now, how do we extract? We don't know any physics. We only have access to data. We know that a mapping between finite dimensions and finite dimensions is bound to be, let's say, measurable mapping. Means everything is measurable. So this will be a DNN. Okay. So nothing fancy happens here. This is going to be a DNN. So just as before. Okay. So the only change so far has been in the encoding. Then we use the processing, and then comes the reconstruction. Okay. So in the reconstruction, what we are going to do is, now we don't know a basis, but we need a basis, right? So the idea behind the reconstruction, perhaps I can write it here, which means that anyone looking at my slides will get brain damaged, but I don't have to look at them again, right? So let's look at the reconstruction. So R, so this is now given the coefficients. So you have these beta k. You are going to process them. I have put some bias here, but this is not essential. You're going to process them by a basis. So beta k tau k, k from 1 to p, right? K from 1 to p. And this tau k now is your basis functions at the reconstruction level. And we don't know what these are, right? So these are functions. We don't know what these are. But since these are functions, what do you think can approximate them? Yeah. So these are functions. Let's say that these are continuous functions. What can approximate continuous functions from data? Neural networks. Come on, now this is anything, just say neural networks and you'll be fine. So these are neural networks, okay? So these are DNNs. So now the basis using DNNs. Okay. So what is the difference now? Of course, there is some difference at the encoding, but the more important difference is that since the basis is unknown, I'm also going to learn it from the data itself. How? This was a question that Shizang asked. After the break, I'll tell you how. But in principle, I can learn any finite dimensional mapping as long as it's measurable. Everything that is one can deal with is measurable. So with the DNN. So what is the sort of workflow here? So there is some extra bias term here. So just to perhaps, it's not essential, but one can also add a bias term so that this is, you can think of it as a basis with one term as 1. Okay, so then this is the reconstruction. So now it turns out that there are 2 sets of neural networks, or 2 groups of neural networks, and they have some names here. So as you can see here, I don't know, it's not yet expanded in the slide. So this one, which takes the encoded values E and produces, so this is the A here, this is called a branch net. And the one which is a basis function. So remember, this Y is an element of D, or the output domain dy. This is what is called a trunk net. Okay. So there are 2 sets of DNNs which are going to approximate the data. And this is where the operator learning aspect comes in, because if it was only, if you had to learn a mapping between vectors and vectors, one neural network is sufficient. But it turns out by taking 2 of them, we can learn an operator, which is a mapping between functions and functions, and we can generalize it. If you want to learn a mapping between operators and operators, you take 2 of these operator approximations and compose them. But that's a different story. So let me just quickly summarize this before we take a break. Or perhaps we take a break first and then I'm going to summarize it. Okay. So the idea, because then you don't, we start with where we are. But the essential thing is 2 sets of neural networks, one doing the finite dimensional processing down here, and one doing the work of the basis up here. You could have had 3, means you could have also taken a basis down here. But okay. This can also be done. This is a generalization of DeepONets. Many of the things fall into this framework. So, okay, but the critical question is, how do we train these things, right? And this is what I'm going to answer after the break. And is this a good idea or not? We will see. Okay, so let's take a break now, and let's be here at 10 past, 12 minutes. And this time I don't forget to. Okay, welcome back everyone after the slightly longer break because of me taking it. Now, let's just summarize what we have learned with respect to DeepONets. Let me add a page. And then I will tell you how exactly to train it. Because this is important, this is a very popular architecture. So DeepONets. So deep is the fact that you're using deep neural networks. So all that these people did in 2020 is that Chen and Chen, they had shallow neural networks. So all these, the two sets of neural networks, trunk and branch, these were shallow, and they just changed that to deep, right? That's their contribution. So DeepONets, so what is the point here is that, so you have, let me write things properly. So you have a mapping G, which goes from X to Y. These are the function spaces. So X is on domain. So the domain here is dx. Because you could have different domains, right? But domain is dy. So these are functions on two different domains. So how do we do it? So in the first step, so on dx, fix point set xi, I from 1 to m. So m is a hyperparameter, and how you fix this point set is also a design choice, okay? And this in particular could be random, or it could be uniform grid points, or something else that you, for instance, Sobol points, depending on how you choose. Okay, so that's the first thing. So the encoding operator E now, so your approximation, okay, let me write it like that. So this takes an input A, belongs to X, and it produces AI, which is equal to A of Xi from I from 1 to M. So this is just a plain vanilla readout of functions at points. Then comes this step here, capital A. So here it takes AI, the vector I from 1 to M, and then maps it through a DNN to beta K, some coefficients, K from 1 to P. And this DNN is what is called a branch net. Okay, so it's a deep neural network, just like before. Also for the spectral neural operators, we are exactly the same. So finally, R, the reconstruction. So you take, so for that, I need what is called another deep neural network, so DNN, which is what is called a trunk net. And what does it do? It takes any point Y belonging to capital Y, no, not capital Y, dy. So belonging to dy, and it maps it to tau k of Y. K is from 1 to P. Okay, so these is supposed to be a basis, although we don't enforce it to be a basis, right? We just say, so these are just DNNs, and this is what is called a trunk net. And what R does is that R of this whole thing is R of beta K tau K, because I need the coefficients as well. This is equal to the summation K from 1 to P, sorry, P, beta K tau K. Okay, and the DeepONet, no talking please. DeepONet D is just the composition of these three mappings. So E, A, R of any input A. Okay, so this is going to be approximation. So at the algorithmic level now, I have two deep neural networks, right? Instead of one deep neural network, I also have these point sets and so on. So is the architecture clear? How I'm going to train? I have a full slide on that, or I'm going to write a full slide on that. But before even going to the training process, is the architecture clear? Yes.
Each TK is a neural.
Each TK is a neural network. Yes, absolutely. So it's a set of neural networks, trunk nets rather. Or you could, for instance, take Y going to TK of Y, right? K from 1 to P. So you could sort of vectorize the operation. So it depends on how you perceive it. You could also say that it's one mapping which goes to, means it's how you write it. So each of them is the output of a neural network. It could be a single neural network, or it could be P different neural networks. Okay, depending on how you choose it. Are there any questions about this? No? Okay, so now we have seen the differences between and similarities between these two different architectures that I just wrote down. So perhaps it's a good time to see how to train them, right? Because this is what is an interesting question. And we will see several other examples, but the training process is exactly the same for all of them. So let me take some time to sort of tell you how, or walk you through how these things are going to be trained. So remember that at the bottom of everything, I have an operator G. So this is a mapping from X to Y, right? So this is what is there, but what I have is data. So in other words, A goes to U, which is equal to G of A. But in practice, and there is also a measure, because someone asked me this question, mu, which is in probability measure. In practice, I have some data. So let me call it as AI is drawn from mu. Okay, so I have a measure on a function space. I'm going to draw this. I'll tell you very quickly how to do this in an example in a bit. But let's say that we know how to draw, just like we know how to draw random numbers or random vectors, we know how to draw random functions, and we can do that. And then my UI is nothing but G of AI plus some noise eta. So this is some noise. In practice, for simplicity here, because this will lead to further complications, let me assume that I'm in a noise-free regime. For instance, everything is done by numerical simulations, rather than the actual lab observations. So now, instead of having access to the operator, I have access to what is called this data pairs or samples. And these are of the form AI, UI. I from 1 to, let's call it as capital N. Okay, so in practice, this is what I have access to. But so far, I'm assuming that each of these things is a function. Okay, you'll see that that will not be that easy to form, but nevertheless, so we have access to these things. Then we have DeepONet or SNO or any operator learning architecture. We will see a few of them. So any operator learning architecture, and this I will call as G star. And what G star can do is that it can take a function and output another function, G star of A, which is equal to U star. Okay, so in practice, I can do that. So remember that there is a measure here. So now I have to, what is the natural difference between the two? What is a mismatch? So a mismatch or an error is, okay, let me call it as a mismatch, because in error, I have to put a norm, right? So I will not do that for the moment. Mismatch between the two could be the following. So let me write it down. So this could be the integral over X, right, of norm of G of A minus G star of A. The norm is, of course, over Y, d mu of A. So this is a quantity. I'm writing everything in function space, but of course, I'm going to discretize it in a second. So let us try to understand this quantity, because it's important to understand what it is. So what am I saying? I'm saying that I am committing an error, right? After all, I'm approximating some object, some ground truth with some model that I'm going to train. And the output of this object for any function A, so I choose a function A, output of the object is going to be G of A. This is the ground truth, the continuous object. And my model's output is going to be G star of A. Remember that I took the liberty to assume that given any A, I can output my model. Okay. So now, of course, these things are objects of Y. So this belongs to Y, this belongs to Y. So in order to calculate the difference between them, I have to norm them in Y. And Y is a function space. We'll do some examples in a bit, but Y is a function space. So this is going to be my mismatch for a particular A. But now remember, I'm drawing my A from some measure on functions. So that's why I'm going to integrate it over that particular measure. Okay, so this is my idealized loss in a way, because this is exactly what we did for finite dimensional objects, except that in finite dimensional objects, we didn't really care so much about the measure because we have a canonical measure, the Lebesgue measure, the Euclidean measure that we have. But other than that, this was exactly a, let's say, function space extension of my finite dimensional objects. Is this crystal clear? Because this is the object that I'm going to discretize in a bit. Okay. So what do? I draw from a distribution all possible functions. That's why I integrated over this particular integral here. And then for each of them, I measure the mismatch. Okay. However, remember that that would be my ideal error or ideal loss, right? So loosely speaking, this is an idealized loss. Idealized loss. But of course, I don't have access to every single instantiation of this particular measure. I only have access to these data pairs, right? So then I have to do something about that. So what do? So now the real loss, or means what is called the empirical loss. Empirical loss is to replace mu, which is my underlying measure, or approximated by what is called the empirical measure. So this is 1 over m, a Dirac mass, a Dirac measure, Dirac distribution sitting at the points ai. Okay, I from 1 to m. So what does this measure? This tells me that I don't have access to, it's like Monte Carlo integration, right? So I want to integrate an integral over this room. I just pick some points in random and say that these random points are good enough to measure the underlying measure, good enough to signify the underlying measure. So if I do this, if I put this and I apply Monte Carlo, this is Monte Carlo on this function integral. Monte Carlo is Monte Carlo, means whether it's in vector space, function space, it's exactly the same. So I'm going to replace this. L now is equal to, so you see, this is I from 1 to capital M. So I have G of AI because I'm drawing this, and this is G star of AI in Y. Is this clear? So this function space integral, I have to use Monte Carlo. There's no other way to do this, but because I'm assuming that I'm drawing things IID from the function space, I'm allowed to make this, and this is equal to UI. Okay, so is this thing clear? So this is, so far everything looks abstract, but we are going to make it concrete in a bit, right? So now I have sort of exhausted my page. I have to add a new page. So instead of having this idealized loss, so remember that now my loss, L loss is going to be L is going to be 1 over m summation I from 1 to m. So this is G of AI minus G star of AI of Y, right? So this is what we arrived at. We replace this integral with the Monte Carlo approximation, but in function space. We can always do that. Good. So now this is what we have, but we are going to approximate this. Well, first of all, this is equal to 1 over m equal I from 1 to m of UI minus G star of AI in Y. And why do I say that? Remember that UI is G of AI, no noise. So I'm assuming that there is no noise in my data collection. The case with noise can be dealt with because you just substitute the UI directly instead of having G of AI. Okay, so this could be noise in this. It's not an issue. So now you have this. So you still have to do an approximation because now I'm stuck with this norm on Y. Norms are integrals, right? And then it's not so easy to deal with integrals. So now I have to make some concrete realization. So let's assume, and this is reasonable because let's assume that Y is equal to some LP of T. Y. Okay, so I'm assuming that I have some LP space. P can be anything. Say P is less than or equal to 1 less than infinity. In particular, P could be 1 or 2. These are the two useful spaces, right? But let's keep it general. Or maybe it's no point in keeping it general. Let's take something. Let's take P equal to 2. We can take P equal to 2 just for concreteness, because otherwise the notation can become cumbersome. So now let us look at this quantity here. So what is this quantity? So let's write it here. So it is UI for a fixed I, because I is the sum here, minus G star of UI, G star of AI in, what is it? L2, for instance, okay? This, let me square it so that everything is easy. And so then it is a sum over dy of UI of y perhaps minus G star of AI y squared dy, right? So this is my definition of an L2 norm. And then I have I can't, of course, compute these integrals exactly. So here I have to use some additional quadrature. Use quadrature. And what is quadrature? Quadrature is given any integral f of x dx is approximated by summation of, now I should use j perhaps. So j from 1 to capital J of omega j f of xj. So this is quadrature, right? So Monte Carlo, for instance, this is 1 over capital J, but you have Gauss, Newton codes, Gauss rules, whatever Clenshaw call it is, this can be whatever, right? So this is what I'm going to do. I'm going to use a quadrature to approximate this integral here. So now this comes slowly, I'm reaching where I want to. So my discrete loss is the following. So this is L. This is given by, so remember that I had my function space 1 over m, I from 1 to m, but now I'm doing a discrete variation here. So this is j from 1 to capital J of omega j, right? And then I have ui of yj minus g star of a also at I at yj squared. So this is the loss function that I have in practice. Okay, so what is the loss function now, and how do we sort of how do we reach this loss function? So it's very important to concentrate on a few things here. So now, what is the training procedure? Maybe I'll keep this. Okay, let me add a page. So before I move on, is everyone convinced that this is the right kind of loss function? There's the only reasonable choice of loss function that we can make, because we did the two approximations that we could. One was in function space, because we can't compute integrals in function space, only Richard Feynman can, right? But and similarly, we have to do an approximation in physical space, because we don't know how to compute integrals exactly in physical space. Okay, so far so good. So the loss that I have to deal with in practice is the following. So let me write it down. So the loss function, loss L, as I said, I'm rewriting it 1 over m of the summation. Now I corresponds to a function space index. So, and j corresponds to a physical space index. J omega j of what did I call it as u I x yj, sorry, yj minus g star ai evaluated at yj. It can get complicated, right? But it's just a wee bit complicated. It's not that difficult. Okay, and what's the algorithm? Somehow, roughly speaking, is the following. Maybe I use a different color. So what do you do in order to do the training? Is given inputs, but I'm still assuming that these are function space values, and there will be a catch, but we'll come to that catch later. Inputs and outputs, or inputs and also the data, is UI, remember? So this is what is my ground truth. And I'm assuming that these objects can be evaluated, particularly the UI can be evaluated at any point. In particular, it has to be evaluated at quadrature points, right? So I'm assuming implicitly that UIs need to be evaluated at quadrature points. So I have that data at quadrature points. So that's why the sort of function space picture is very clear. I should have a function that I'm going to evaluate. At the output level, at the input level, this does not come into the loss function, as you can see. Yes, go ahead.
If we only have one pair, so one A, one B, we could feel it like a loss term, but I don't know, because I don't know much about the but we couldn't assume that our operator G star works on the whole function space, because then we
No, I got your point. Of course, if you have only one input-output pair, it's like learning, or it is it's only one sample, right? So you can also say that I want to fit a line from one point, and we can't fit a line from one point. So now you're saying that we want to do this in infinite dimensions, right? And this is, of course, we are not going to do that, because this Monte Carlo error, as I've told you repeatedly, this decays as 1 over square root of m. So also in function space, it is going to decay as 1 over square root of m. So if I take m equal to 1, my error is roughly order 1. So I learn nothing. If it's 10,000, then it is 1%. If my constants, my variance is going to be of order 1. Okay. So of course you can try with one input-output pair. Sometimes you can be lucky that exactly with one input-output pair, I could learn something. If anyone wants to think about it, think of an example where I'm able to learn also in finite dimensions, but certainly in infinite dimensions, from one input-output pair a whole operator. You can do it. It's not impossible. But think about it. I'm not going to tell you the answer. But in practice, as you see, we need quite a lot of data. Okay. So one is also completely okay in this theory, but it leads you nowhere. Okay, so this is important. So I have these are my inputs, right? And then what do? I have the inputs. Then I have to run whatever operator architecture, DeepONet. Let's use DeepONet as my proxy, right? Run DeepONet on AI to obtain G star of AI. And remember, it's essential that G star of AI can be evaluated at the quadrature points, at xj or yj, sorry. So then, you run the algorithm. So for each instantiation, you run the algorithm. You extract these values here, you compare them, you form this for each sample, and then you sum over all the samples, essentially form the mismatch or compute the loss term per sample and sum over samples and sum, right? So this is going to be your loss function. So at each step now, this you're going to train with gradient descent, right? Because how else are we going to train it? Because what are our free parameters? Our free parameters are here. They are sitting here in this G star. Because remember that in my G star, for instance, if I have DeepONet, where is it gone? Yeah, so here I have my weights and biases here, and I also have my weights and biases in the trunk net. So on both sides, I have my weights and biases, and these things are going to be now trained from simultaneously. So the basis as well as the coefficients of the basis, they are going to be inferred directly from this training process. So for each iteration of gradient descent, I have to compute these objects. So I better have my data and I have my evaluation and then just loop through. Okay, so this is the algorithm. It's a little, it's not plain vanilla neural network training. There is a little bit of, because of this double summation. Because if I did not have a double summation, it would essentially be training one neural network or one sort of vector-to-vector neural network. But in operator learning, you have to do this double summation, essentially. But again, there is an assumption that everything here is sort of function valued, and I have evaluations of the functions available at every point, which is also true in DeepONet. If you remember, in DeepONet, the input is fixed at a certain points, right? A fixed number of points, but the output is available at any point because we are reconstructing the basis. It's the same with SNO. With SNO also, the output is available at any point because I have a basis reconstruction. So it's essential to have this kind of basis reconstructions, because in the training, you're going to need them. Okay, so this was the training procedure in a nutshell. I think in one of the tutorials, one of them, Victor or Emmanuel, are going to show you, Roberto are going to show you how to do this in practice. And I don't want to spend further time on that. But it's not that complicated. It's a little more than standard neural network training. Questions? Now you're convinced, so Shishang, how the training is done? Or someone else asked me a question during the break about, what did you ask me? What did you ask me about the measure, right? And the fixed number of points. Yes, so this is a good question. So as you can see, there are many hyperparameters in addition to the what sort of architecture I'm going to use for the trunk net and the branch net and so on. I also have hyperparameters like M here, P, and so on. I'm going to explain that can only come from theory, right? Means how else are we going to fix those things? We can either do trial and error, or we have to find some theoretical basis. But that is going to come in a bit. Any further questions about the training? No? Okay, so if there are no further questions, let me just very quickly, where is the, yeah. Okay, so now you can imagine that by using this sort of framework, you can generate many different types of neural or this kind of operator learning architectures. As I told you, this is not how it was done historically. It means if you read the paper of Chen and Chen, the original paper, there is no mention of numerical methods, there is no mention of basis, there is no mention of any of these things. These are our, or especially my own interpretations on what is going on here. This is what is roughly going on. Many of these architectures can be understood in the same conceptual framework, and we can churn out new architectures accordingly. So perhaps without going too deep, maybe I just to think a little bit about time, because okay, maybe I very quickly tell you about PCA-Net, which is another architecture which is widely used, and this is slightly different from DeepONet and SNO. But before that, how many of you know what is PCA? Raise your hands now. PCA. Not everyone, but quite a few people know what is PCA, right? PCA is a very basic algorithm on. So so PCA is essentially a sort of a, let's say, dimension reduction algorithm, we could say. Dimension reduction, data-driven dimension reduction algorithm. I'm not going to give a lot of details of that, but just very quickly, what it does is, maybe I'm too slow now, but I need to move on a bit, otherwise I'll finish nothing. So the idea is the following, that remember that at the end of the day, you have this E operator here, encoding. So this will be a PCA, or this will be essentially a PCA, and R here will also be based on a PCA. So, and this is going to be based on a DNN. So earlier, so with DeepONet, we were doing with SNO, we are fixing the basis. With DeepONet, we were learning the basis at least at the output, whereas at the input, we were just taking point-wise evaluations, which actually, if you take a nice enough set of points, is fixing the basis. Here, instead, we do a PCA. PCA is sort of finite dimensional, well-defined algorithm. Let me very quickly cover it, just very quickly, so that. So what is the? So let me start with finite dimensional PCA, and then the function space version of it is also very straightforward. So the idea behind PCA is the following: that you have been given data pair or given data, let me call it by VK, so K from 1 to capital K. Okay, and VK itself can be in D dimensions. It could be a vector, but I'm not going to, yeah, so it's just a vector. So now K could be large. So this is just imagine data, for instance, discretizations of your function that you have been, or functions that you have been given, right? And the idea behind PCA is to project. Project is a bad word, but it's roughly a projection. Project data onto a more convenient basis. Again, basis comes in many times onto a more convenient basis. Okay, so this is sort of the basic idea. So in other words, let me call this more convenient basis as W perhaps, because now I've used Q, and let's use it as J as my index, J from 1 to J. And what I'm going to do is that J is much less than K. This is often the way we think of PCA, right? We take something in 100 dimensions and we reduce it into 2 dimensions and things like that. So we do some dimensional reduction that way. And the idea is very simple. The idea is that you're going to write, so for each Vj, so you're going to write each Vj, Vk as some beta kj, wj, j from 1 to capital J. Okay, so you are going to write a basis where the beta k is the coefficient and your wj's are the basis functions or basis vectors in this particular case. And there is a natural minimization problem. So you minimize essentially beta j, wj, such that summation of k from 1 to capital K, Vk minus, so this is a projection, right? J from 1 to J, beta k, j, wj squared. So there are 2 double summations similar to what we saw in operator learning. There's a summation for each data point, and there is a summation over the whole thing. You could normalize, right? So you want to minimize, and this is well-known result in linear algebra. So this corresponds to an SVD, a singular value decomposition on the matrix, on the covariance matrix. I'm just assuming that Vk is 0 mean, because otherwise I put just the mean of the data, 0 mean data. So covariance matrix, which is given by summation of k from 1. Some people call it as a snapshot matrix, but I prefer to call it as a covariance matrix. So this is a tensor product, is in the vector dimension. Okay, so you take like v1 squared, v1, v2, v1, v3, and like that you form the matrix. Now you have this set here, this so-called snapshot matrix, and you take its SVD and you truncate it. So lambda, now give me another L, for instance, and phi L. Now phi is not a good notation here, but because that's reserved for function spaces, right? Lambda L, WL are the 1 less than or equal to L less than or equal to, what did I call it as here? Didn't I say J? J leading singular values and vectors. Leading singular values and vectors. So this is PCA. So your beta J is now lambda L and WL. So this is what represent your entire algorithm. So in other words, what does PCA return? PCA returns that you have Vk can be approximately written as summation over lambda L and WL, L from 1 to J, and these are your singular values and vectors, right? So essentially PCA amounts to just doing a SVD, but no one writes this from scratch. All packages, SciPy, for instance, is a very good singular value decomposition. So now in particular, so what is the relationship? So this is PCA. There is a function space version of it. This is what I wanted to say. So there's a function space version. And this is given by the sort of, now it's no longer singular values, and it's still singular values and singular functions now. Singular functions rather than singular vectors of the covariance operator. So there is, it's almost mutatis mutandis, 1 by 1 or 1-to-1 transferable to the following. So V is drawn from your measure mu of V tensor with V. I'm assuming 0 mean. So this is what is called the covariance operator, which is a function space version of PCA. And this is also a very well-known algorithm. Of course, in practice, you have to discretize, but this can be done. Okay, so now what is my PCA-Net? PCA-Net is the following. So PCA-Net is that you take, so you have your inputs. Inputs are given by AI, right? I from 1 to, what did I call? M. Okay. So do a PCA, and you extract your sort of coefficients, PCA coefficients. And then from there, also on the output, you do the same, do an output PCA. And so this will also give you some basis, right? So on both sides, you have some basis because PCA gives you these coefficients. So these are the input coefficients. This is what you process, and then use the singular vectors or singular functions to reconstruct. Okay. And so this is the algorithm. In between, you do this processing, right? So the advantage of PCA is that PCA itself is sort of a data-driven algorithm. So it provides you potentially a better basis than fixing the basis. Also, it provides you, because it's sort of a quote unquote linear algorithm, you're not having another set of neural networks to train. It's probably a good preconditioner or a good starting point to use DeepONets. So PCA can be used on both sides to extract coefficients, and then you process them through a deep neural network. Okay, so this is somehow in between what we saw with DeepONets and SNO. Because in SNO, you fix the basis. In DeepONet, you learn the basis entirely from data. Here, you also learn it from data, but you learn it in this sort of projection manner, as if it is a basis, right? Because in DeepONet, you have no guarantee that this is going to be a basis. So many people also use this algorithm. It is, for instance, proposed. Again, all of these are, as you see, very recent algorithms. This has been proposed in the recent paper. It turns out that all these algorithms perform relatively well. There are issues with them. We will touch on the issues in the next lecture. All of them perform relatively well. Here is an example, and I will end with this example because I thought that I will show you the limitations, but I'm always slower than what I expect. Okay, here is an example. It's a very simple. We will do extensive examples in a couple of lectures, but just to set the stage, let's take a simple example. So it's a forced pendulum. Everyone who has done high school physics knows what's a forced pendulum. So I have minus u double prime is equal to sine of u. I'm taking the mass and all the constants to 1 plus some a of t. Okay, so it's a ODE, it's a nonlinear ODE. And so this is my forcing. And my u is my displacement. Angular displacement, but displacement nevertheless. And this is essentially Newton's law, right? The rate of change of force, the rate of change of acceleration, rate of change of velocity equals force. Okay, so how do I set this problem up? So what I do is, remember that in my training process, I had to fix this measure, mu, right? So this is the measure from which I'm going to draw my samples. So what you could think of various options. We will think of various options during the course in the next couple of lectures. But a very natural candidate is to use what are called Gaussian random fields, or in this particular case, Gaussian processes. Has Ben spoken about Gaussian processes in any of in the tutorials? Has this been covered? No. Gaussian processes are sort of extensions of normals or Gaussian distributions to functions, right? So, for instance, you want to, so this, let's say the input A is drawn now. This is the notation from a Gaussian process with mean 0 and with covariance kernel KL. Okay, so this is what is called a covariance kernel. If you draw from a Gaussian measure, a Gaussian function, then this is a covariance matrix, but now it has to be a kernel. And this kernel is usually given in the following manner. T1, T2 is roughly, well, exactly, because I could forget a normalizing constant. This is a negative exponential of T1 minus T2 squared by 2L squared. L is what is called the correlation length. Okay, and there are many algorithms. If you go to Wikipedia or ChatGPT or whatever Google search, and you find out how to draw from a Gaussian process, there are tons of codes that are available. Actually, ChatGPT has very good code because I checked it the other day. I was lazy to write something, so I said, okay, give me a Gaussian process of this correlation kernel, and it was quite okay. So now this is it's, as you can see, it's an extension of just a Gaussian on multivariate Gaussian, right? So instead of having, you have function space values in this particular case, so we can draw from it. So here is how a draw looks like. And then we generate, we use a numerical ODE solver. A very accurate one. I think it is Runge-Kutta 4. I don't remember what was used in this. Probably Runge-Kutta 4. Very accurate solver. And then we generated. This is done with respect to 1,000. This is an example. I think it is 1,000. I could be wrong. So M, the number of samples was 1,000 samples. And this is so we do the training of these inputs, and this is how the output looks like. So as you can see, the predicted, this is with the DeepONet. It's a very simple problem because everything is smooth. The functions, the input functions are smooth, the output functions are smooth, but it does a good job, right? Because the error with DeepONet is less than, it's nothing, it's 0.35%. And with PCA-Net, it's 0.18%. Okay. In this particular case, PCA-Net was better than DeepONet, but it doesn't mean much because these are small errors. So what is the difference now? The difference is my input and output are functions, and I'm able to learn the sort of mapping between them by doing this, right? So this is already encouraging. But in the next lecture, we will see that there are still several skeletons in the cupboard here, right? Because we don't know what the different hyperparameters are. Just by doing a couple of numerical experiments, we cannot ascertain whether the method is working or not. And there are some theoretical issues. And this will force us to look for alternative architectures, because this was a very positive one where DeepONet and PCA-Net was like 0.1, 0.2%. But remember that the example that I had with the shear that I showed you last time, the CNN, right? So there I can tell you that DeepONet is like 15% the accuracy, and PCA is like 25% or something. So these things are not universal. This is just to illustrate. But why this happens, we talk about it in the next lecture. Okay, so we stop here and